Hello everyone, this video is for reviewing KTCE math exam whose employment year is 2024. KTCE stands for Korea Teacher Certificate Examination, which contains interest problems of college level. Anyone who wants to work at middle school or high school, either in public or private in Korea, has to pass this exam. They are supposed to pass this exam. On this video, I'm gonna deal with specifically the statistical problem number 11 from the type A exam paper. This is about random variable basically, and it is related to figuring out its probability density and its occurrence probability. Okay, the first point of this problem is the relation between its probability density function and the accumulative distribution function. Usually, in general, the probability density function is a non-negative function on its domain, okay, and the cumulative distribution function is usually written with a capital letter, capital F of x here, which stands for the sum of all the probability whose random variable is equal or less than x here. So it is an integration of the probability density function from negative infinity to x. Okay, so for instance, let me give you a brief relationship between those two. Okay, so in case of normal distribution, let me simplify with mean 0 and some variance sigma square. Its probability density function will look like it will be a symmetry with respect to x equals 0, and it's a bell shape. And then it's a whole area. If I integrate it from negative infinity to positive infinity, will give us 1. That means 100% as a percent. By the symmetry, each half of each area contribute to 0.5. Okay, so this half and this half, their area will be 0.5 each. Okay, and when I think of its cumulative distribution function, capital F of x, and then it has a certain property from its probability density function. So since it is symmetry and their area of each half is 0.5, so in this case it passes through a 0.5 when x is 0, so which stands for integration from negative infinity to 0 of its probability density function is 0.5, so I denote it as capital F of 0.5. Okay, so this is a graph for y equals capital F of x, which stands for its cumulative distribution function, and its upper bound is 1. So let us think its speed of increasement. Okay, as x goes from here to here, as x approaches to 0 as a negative value, and then its value of probability increases, so that means the speed of increment is increasing here, so that means it's a concave down. No, I'm sorry, this is a concave up. And as a positive value, as x increases, it approaches to infinity, it keeps increasing, then the value of its probability decreases. So that means the speed of increment is decreasing on this right half side of this graph. So this graph looks concave down. So this will be graph of its cumulative distribution function, and obviously, as you can see, the value of its cumulative distribution function takes value from 0 to 1. Okay, and another non-trivial fact is that when we take a derivative, the cumulative distribution function with respect to random variable x, and then we'll have a probability density function. This relationship comes from this integration form of a cumulative distribution function. Okay, so when you take a derivative with respect to x, then we'll have small f of x here by Newton's formula. Okay, let me erase this part. Okay, so let's directly dive into this problem. The second point is to take a new random variable. I call it capital Z, which stands for capital F of capital X here. Okay, and I'm gonna consider the accumulative distribution function of this new random variable z, that is the same as probability capital Z is equal or less than small z here. So that will be our accumulative distribution function of this new random variable. And let me note that since this is a accumulative distribution function, the random variable can have value from 0 to 1 here. This is a short remark. And then since capital Z is nothing but capital f of x, which is equal or less than small z, this function gives us 1 if the small z is equal to 1 or greater than 1, because the range of its new random variable has a maximum 1. Okay, and this accumulative distribution function will have a value 0 if this small z is negative here. So what we are interested is when small z lies between 0 and 1. Okay. Okay. As I recall, the shape of graph of this accumulative distribution function y equals capital F of x has a value between 0 and 1 here, and roughly it's an increasing function. That means its derivative with respect to x is non-negative here. Actually, this is a probability density function which is non-negative. Okay, so when the small z value is between 0 and 1, let's say this value, and then there's some random variable x which corresponds to this small z, such that its accumulative distribution function of this probability density function from negative infinity to positive infinity equals to z. Okay. In this case, let me call this. I abused the notation. I'm sorry. I abused the notation x too much here. Let me change it to notation t here. F of dt and dt. It looks better. Since it's increasing function, let me call the inverse image of z as a capital F inverse of small z. Okay. So when z lies between 0 and 1, the probability will be the same as when capital X is equal to or less than F capital F inverse of small z here. And this is nothing but capital F inverse of z, and that's a identity function. So its value will be small z here. Okay. So in this case, the probability density function we don't know yet, but the graph of a cumulative distribution function of capital Z looks like from 0 to 1. This is linear, so when it is 1, it takes value of 1, and when it's less than 0, capital of Z, its value is 0, and between 0 and 1, it's y equals z in this part, okay? Okay, so to figure out the probability density function of this random variable capital Z, we take a z derivative of this graph, and then it will give us this graph. Y equals capital F prime of Z. When capital Z lies between 0 and 1, its value will be 1 here. And this is not continuous at this point of z equals 0 and z equals 1. And when z is greater than 1 or less than 0, its value is 0. So the probability density function with respect to variable z will be 1 when z takes value between 0 and 1. Let me remove its ending point. For the continuous variable case, removing 1 point or adding 1 point more, it does not matter. And then it will have a 0 value otherwise. Actually, this is, so capital Z follows a uniform distribution from 0 to 1. Okay. So this is our first point. And for the second point of this problem, find the specific probability value of this. And I claim that this is rather straightforward, so I'm not gonna do the whole computation for you because I believe you can do it. So on this probability of ln of capital F of x, since ln of capital F of x is increasing function, capital F of x should be between e to the negative second power and irrational number e, natural constant e here. And since they are positive value, and this natural constant is actually greater than 1, so uh, let me point the value of e to the minus second power, and it's a natural constant e, which is approximately 2.7 here. So it corresponds to here e to the minus second power and natural constant e. So probability of x, which lies between this f inverse of e to the minus second power and capital F inverse of natural constant e is the same as so its inverse value will be the same as e to the minus second power, and the inverse value of actually there's no inverse value, but it has an inverse image as 1 here. And you can think that you know that this is a uniform distribution on the interval from 0 to 1, so its probability is length of this interval, 1 minus e to the negative second power. Okay, let me wrap up this problem. The point of this problem, to me, it looks that it's a change of random variables. So you got a new random variable, and if you want to find probability density function of this new random variable, you can directly obtain it if you are able to do that. However, in general, this is not so easy. So in my case, I first think of its accumulative distribution function of the new random variable first, and then take a derivative with respect to new random variable, and then that will give me probability density function of a new random variable. Okay, this is all.